Another example, consider R3 and R2. For R3, we consider the ordered basis S as shown. So this is not the standard basis for R3. For R2, we use the ordered basis T as shown, which is also not the standard basis. Let us suppose that L is a linear transformation from R3 to R2 such that the matrix of L with respect to S and T is already known. So let's say its matrix with respect to S and T is given by matrix A as shown. Using this, we can find the function values of 2, 1, negative 1 under L and the function value of a general vector from R3 under L. We simply use this formula that to obtain the coordinate vector with respect to T of L of V, we just multiply A to the coordinate vector of V with respect to S. This holds for any vector from the domain. So to answer A, first we have to find the coordinate vector of 2, 1, negative 1 with respect to S. So we have to find scalars R1, R2, R3 such that 2, 1, negative 1 is equal to this linear combination with scalars R1, R2, R3. But of course, this linear combination can be written as a matrix product. So we solve this system by Gauss-Jordan. I will leave the details as an exercise. You can find that R1 is equal to 2, R2 equals negative 1, and R3 equals 4. Okay, so from this, we obtain the coordinate vector of 2, 1, negative 1 with respect to S. 2, negative 1, 4, coming from these scalars. And so, by our note at the beginning of the solution, the coordinate vector with respect to T of the image of the given vector under L is obtained by multiplying 2, negative 1, 4 by matrix A from the left. And you can check that the result of this multiplication is the 2 vector with entries for negative 3. So this is the coordinate matrix, or rather coordinate vector of this guy with respect to T. So from here, we can determine the function value of L of 2, 1, negative 1 using the vectors in T. The vectors in T are 1, 2, and 1, negative 1. So we just form the linear combination of 1, 2, and 1, negative 1 with scalars 4, negative 3. So this operation will give the 2 vector with entries 1, 11. So this is the function value of 2, 1, negative 1 under L. For B, we just apply the idea in used in A for an arbitrary vector from R3. So first, we have to determine the coordinate vector of xyz with respect to S. So we need to find scalars A, B, and C, which are in terms of x, y, and z, satisfying this linear system. So again, we can solve this by Gauss-Jordan. I will leave that as an exercise, but you should be able to obtain ABC equal to the 3 vector y minus z, z, x plus y minus z. Okay, so ABC are scalars in terms of x, y, and z. So from this, we obtain the coordinate vector of xyz with respect to s. So this guy is the coordinate vector with respect to s. So we just plug this into the equation. So using this, we can now determine the coordinate vector of the image of xyz under L with respect to t. Okay, we just multiply a to the coordinate vector with respect to s of the given vector. So plug in the values for matrix A, and for the coordinate vector, we obtain this whose product is equal to the two vector with entries x plus 2y and negative y plus 2z. And finally, to obtain the function value of L at xyz, we just use the vectors in T. So we form the linear combination x plus 2y times the first vector in T plus negative y plus 2z times the second vector in T. So we just applied, or we just used the components in the coordinate vector. And this gives the two vector with entries as shown.